geometric design process is a forward-looking. Road infrastructure is designed and constructed to accommodate the future transportation needs. Right-of-way purchase for transportation is removed from other productive use. Well-constructed and maintained major urban road or bridge should last for 75 years or more. Right-of-way acquired may be the maximum available into the future, depending on how the adjacent land develops and matures over time. The value and utility of right-of-way will last for 100 years or more. This guiding principle is not new, but its implications are often overlooked by the designers. A forward-looking process contains built-in uncertainty. Actual traffic will differ from travel demand forecast. Unforeseen changes in the context will occur, and road designed, usually models, will not always perform as expected or intended. Such uncertainty cannot be overcome with additional data, greater investment in technology, or more details in engineering. The amounts of uncertainty and the implications of the different features emerging will vary widely based on the local and regional context. The land use in many urban areas is fully built out and stable. Also, certain project types are inherently more uncertain in their outcomes than others. New roads, new major urban roads, or new alignments are clearly the most difficult to forecast the future. The new roads will generally affect the land development patterns in very significant ways. They will change commuting, freight movements, and other travel patterns. Major new roads may significantly impact on regional development in a way that influence the road network beyond the project itself. Safety predictions and operational models based on research elsewhere may be applicable to new roads, but the extent to which actual outcomes mirror modeled ones is inherently uncertain. Reconfigured and reconstructed roads may produce some level of uncertainty in future traffic patterns if they include substantial increased capacity. Such projects may result in intensification of abutting land use and regional travel pattern shift. However, reconfigured and reconstructed major urban roads will generally produce more predictable and less severe changes in traffic patterns than the new roads on the new alignments. Reconstructed roads in their current configuration will generally produce little measurable change in patterns or volume of traffic. Post-construction outcomes will be more predictable from the safety and operational perspective. A significant design process challenge regarding future uncertainty is the conflict between typical nominal design year for infrastructure and usually physical life of such infrastructure. Major urban road projects are sized based on forecast travel demand, which reflects forecast on land use, local and regional socio-economic change, evolution in social trend related to transportation, and national and local policies. Travel forecast typically reflects a minimal 30 years time frame from initial study, which represents a consensus maximum ability to forecast the cumulative effect of the factors that I have mentioned on travel demand. Complex and substantial projects can take up to 10 years or longer from original planning phase to construction, thus frequently resulting in a project size to meet a little as a 20 years future post-construction time. This contrasts with the useful life of a new constructed pavement, bridges, and other infrastructure, with at a minimum of 50 years, and depends on many factors that may be as great as 100 years. The geometric design process for the major urban roads must address and reconcile differences in a time frame associated with ability to forecast future demands and needs, and the intent of the infrastructure investment to be more long-term lasting. This is specifically true for the new construction and reconstruction projects. The fundamental principle number 5, design process must be context sensitive to the extent possible and financially sustainable at both program and project level. The geometric design process needs a more robust set of context definers, and design process should support or direct design decisions, dimensions, and choices consistent with the defined context. The 21st century has been the continuation of trends earlier established and emerged of new challenges. The continuation of fuel efficiency placed more permanent limitations on fundings for road improvements. Aging infrastructure became the primary problem facing the various road agencies. Therefore, it was apparent that a new approach should be developed, and in particular, new alternative design concepts should be established. The various Department of Transports and the road agency came under the considerable pressure to explain their programs to explicitly include pedestrian and bicycle infrastructure. The Austroads guidelines are fundamentally a collection of quantitative geometric design criteria and qualitative design guidance that does not present any particular design process. The current geometric design process, with the operational and particular safety effects of geometric design principles, were poorly understood. In the past 25 years, there has been an increasing industry movement towards greater flexibility in design to help projects meet the needs of multiple stakeholders. This flexibility has become easier to justify on a project-by-project basis as knowledge about previously unknown traffic, operational, and safety effects has advanced. As the range of stakeholders' view about road projects and the industry movements towards flexibility has expanded, a number of alternative design concepts have become part of design practice. One of the alternatives is a complete street concept. Another one, concept of context-sensitive design. The third one, concept of performance-based design. Fourth, concept of practical design. Fifth, design metrics approach. Six, safety systems approach. 7th, concept of travel time reliability. And 8th, concept of value engineering. So what is this complete street concept approach? It focuses on creating a roadway and related infrastructure that provides safe travel for all users. The goal to consider all transportation modes in the design of urban roads, including bicycles and pedestrian needs. The complete street concept considers all transportation modes and all travelers. Typical elements: sidewalks, bicycle lanes, shared user paths, designated bus lanes, safe and accessible transit stops, frequent and safety crossings for pedestrians. Concept of context-sensitive design, known as context-sensitive solutions, places priority on assuring that road projects fit the context of the area through which they pass, put projects' needs as well as the values of the Department of Transport or road agency and community on a level playing field, and considers all trades-off in decision-making. The goal: to achieve that each project is designed in a manner consistent of roadways, strong community, neighborhood, and the environmental values. Concept of context-sensitive design. It is guided by 4 core principles. Strive towards a shared stakeholder vision to provide a basis for the decision. Demonstrate a comprehensive understanding of the context. Foster continuing communication and collaboration to achieve consensus. Exercise flexibility and creativity to shape effective transportation solutions while preserving and enhancing community and natural environment. Concept of performance-based design incorporates a design process that considers explicit considerations of performance measures, operational and safety performance. The goal: to explicitly consider operation and safety performance measures in the design process to achieve specific operation and/or safety goals. Concept of practical design focuses on addressing only improvements that are needed and eliminates those improvements that are not absolutely essential, reducing the overall cost of the project. Goal: to relax specific design criteria to minimize project cost, consistent with achieving other stated goals. Design metrics approach includes 3 levels of design for road projects: basics, modified, and full level. Goals: to achieve a required level of accuracy in the design details and overall construction cost. Safe systems design takes a holistic approach in that the responsibility for road safety is shared between all facets of the transportation system: infrastructure, roadway users, and the vehicles. Goals: to design each project so that motorists will choose to travel at speed that the designers consider the appropriate to crash risks present on the roadway.